There are instances when the limits of an equation result to forms which are unclear or indeterminate. One can still determine answers using derivatives. Welcome to differential calculus. In case we get 0 over 1 when determining the limit, we know that the answer is 0. Flipping the numbers into 1 all over 0, we get an answer of infinity. But how about if we get 0 all over 0? Do we treat this as 1? It isn't possible. Hence, 0 all over 0 is one of the indeterminate forms. On the other hand, if we have 0 over infinity, it is clear that we got 0. And with the case of the reciprocal, infinity all over 0 is infinity. However, we keep it as indeterminate when we end up with infinity upon infinity. The next group of indeterminate forms include the products. At first, if we end up with 1 times 0, or the other way around, we still get 0. Also, with 1 times infinity or vice versa, we still get infinity. But how about 0 times infinity? This form is a type 2 indeterminate number structure. Let's check the other type 2 indeterminate form. For instance, the result ended up as infinity plus infinity. This, we are sure that the result will be a greater infinity. But how about the opposite operation? If we have infinity minus infinity, we keep this as an indeterminate form as we aren't sure which infinity is bigger. Type 3 indeterminate forms include exponents, and they are 1 raised to infinity, 0 raised to 0, and infinity raised to 0. In order to determine indeterminate forms, we would have to use L'Hopital's rule, which states that if the original form of the equation turns out as indeterminate, transform the expression into derivatives before plugging the limit. In case we get the limit of the function of x over another function of x, we would take the derivative of the numerator and also that of the denominator, and just the same plug the value of the limit. In the format alone, it is quite obvious that the rule only applies to quotient, as it requires the derivatives of the numerator and the denominator. In this video, we will practice evaluating the limits of type 1 indeterminate forms. First, let's find the limit of sine of x over x as x approaches 0. If we plug 0 into x, the expression turns out as sine of 0 all over 0, where sine of 0 is also 0, giving us a result of 0 all over 0, which shows that this is a type 1 indeterminate form. Let's transform the limit expression into its derivative using L'Hopital's rule. So, the derivative of the numerator, sine of x, is cosine of x, and the derivative of x is 1. With x as 0, we get cosine of 0 all over 1, which is then simplified as 1 all over 1. So we can say that the limit of sine of x over x as x approaches 0 is 1. The next example has the limit of e raised to 2x minus 1 all upon x as x approaches 0. Plugging 0 as x, we get e raised to 2 times 0 minus 1 all over 0, which turns into e raised to 0 minus 1 all over 0. Now any number raised to 0 makes it 1. So have this subtracted by 1 and divide everything by 0 makes the result 0 all over 0, a type 1 indeterminate form. We use L'Hopital's rule in an attempt to find an answer, so the numerator would have the derivative of e raised to 2x minus the derivative of 1. The denominator will have the derivative of x. The derivative of a constant is 0, and the derivative of x is just 1. So we simplify the expression as e raised to 2x times the derivative of the exponent 2x upon 1. Now, the derivative of 2x is 2, reducing the expression into 2 times e raised to 2x. Plug x as 0, so we get 2 times e raised to 2 times 0, which in turn becomes 2 times e raised to 0. And again, e raised to 0 is 1. Thus, we can say that the limit of e raised to 2x minus 1 upon x as x approaches 0 is 2. Example 3. We have the limit of x squared plus 3x minus 4 upon x minus 1 as x approaches 1. We place 1 for x, making the limit 1 squared plus 3 times 1 minus 4 all over 1 minus 1. Simplify the operations to get 0 all over 0. Thus, we needed to use L'Hopital's rule here. Start by taking the derivative of the numerator, that is the derivative of x squared plus 3 times the derivative of x minus the derivative of 4, all over the derivative of x minus the derivative of 1. The derivative of x turns out as 1, and the derivative of a constant becomes 0. So we get the derivative of x squared as 2x with 3 upon 1. With the expression already simplified, plug 1 as x to get 2 times 1 plus 3 all over 1 to get 5. This is the limit of the whole expression. Alternatively, we can evaluate the expression using factoring. The numerator can be factored as the quantity of x minus 1 with the quantity of x plus 4. By doing so, we can cancel x minus 1 from both numerator and denominator, leaving us with x plus 4. So if x is equal to 1, we get 1 plus 4, which gives 5, the same answer using L'Hopital's rule. There are also cases that we would need to take multiple derivatives to arrive at an answer. Example 4 will just show that. Say we need to look for the limit of ln of 1 plus e raised to x upon 5x as x approaches infinity. Plugging infinity as x, we get ln of 1 plus e raised to infinity upon 5 times infinity, whereby ln of infinity over 5 times infinity will result to infinity over infinity. Using L'Hopital's rule, we take the derivative of the numerator, that is, the derivative of ln of 1 plus e raised to x over the derivative of the denominator, 5, times the derivative of x, which we take as 1. Now, the derivative of a natural logarithm turns out as u prime all upon u, which can be written as the derivative of the quantity 1 plus e raised to x over u, that is 1 plus e raised to x. Then attach the main denominator 5. We can further work with the derivative of the terms in the numerator as the derivative of 1 plus the derivative of e raised to x. Again, the derivative of a constant is 0, so we finally have the simplified expression e raised to x upon 1 plus e raised to x all over 5. Arrange the terms to have the main numerator as e raised to x and the main denominator as 5 times the quantity of 1 plus e raised to x. With the simplified expression, we plug x as infinity, so we get e raised to infinity over 5 times 1 plus e raised to infinity. E raised to infinity is still infinity, so we end up with infinity all over 5 times 1 plus infinity, which can be reduced to infinity over infinity. We have exhausted first derivative using L'Hopital's rule, but still ended up with an indeterminate form. So we try to find the second derivatives of the numerator and denominator. From the original equation, we take the derivative of e raised to x over 5 times the derivative of the quantity 1 plus e raised to x. The derivative of e raised to x is the same e raised to x. Distribute the derivative in the denominator to get 5 times the derivative of 1 plus the derivative of e raised to x. The derivative of 1 is 0, so we simplify the expression as e raised to x over 5 times e raised to x, where e raised to x can be cancelled out. Thus, the limit of the ln of 1 plus e raised to x upon 5x is equal to 1/5. Check out the last example, where we have the limit of tangent of x over x as x approaches pi. Plugging pi as x, we get the tangent of pi over pi. Tangent of pi is 0, so the expression turns out as 0 all over pi. At this point, we cannot use L'Hopital's rule as the form is at 0 over 0. Furthermore, 0 over pi is just 0.